Good afternoon, Year 9. Hope you party people are all okay. Today we're going to look at Boolean logic and processing, which sounds intimidating, but can be summed up by saying we're just going to look at the CPU. Lesson objectives today are, number one, to be able to know what the CPU is and what it does. What it does is the hard part, to explain the fetch, execute cycle, and then the factors that affect the CPU's performance. That's the easy one, really. Quick challenge, 30 seconds, so pause the video because I'm not going to hold it for 30 seconds, but can you write down as many input devices as you can, and can you write down as many output devices as you can? I'll give you a clue. The list of input devices should be longer than the list of output devices. So I'll leave you to pause it, have a quick go. If you want, include it on your submission to show my homework, little screenshot, whatever, or picture of your handiwork, that's fine. Right, what is the CPU? CPU stands for Central Processing Unit. Basically, it's the brain of a computer. The main function is to fetch and then execute the instructions that it gets from us, the humans who control them. The process is known as fetch, decode, execute cycle. If you have done this or chosen to do this at GCSE, you will hear that a lot. You will be expected to know it in quite some detail. But this is what we're going to look at today. So I do apologise that today's video is going to be a bit longer, as there's a bit coming up shortly that will require quite the explanation from me. Right then, features of a CPU. Number one, the clock speed. The clock speed of a CPU is how many fetch, decode, execute cycles that can be run per second. Each cycle runs one instruction, so it could be also be described as how many instructions are run per second. Clock speed today is usually measured in gigahertz. I'll give you one example. The laptop I'm using to make this video has a clock speed of something like 2.5 gigahertz, something around that. The first computer I ever used had 14 megahertz, which is significantly slower. But we'll get on to a little bit more detail on that on the next slide. Excuse me. So then, features of a CPU, the number of cores. This is one aspect that affects the overall performance of a CPU. The clock speed, like an engine size, is basically raw horsepower. The faster it is, the more it can do per second, therefore it is quicker. But also, CPUs come in different varieties and flavours. Single core CPUs are kind of out the window now. Dual core, I believe the machines at school are dual core. Don't quote me on that one though. It might be quad core. Not that it really matters. 2 cores, 4 cores. The CPU in my personal desktop machine at home has got 6, and the mobile phone I'm using to record my voice now has 8. Each core runs its own fetch, decode, execute cycle, so the more cores we have, the more programs or instructions we can run at any one time. It's a bit misleading to say how many more programs you can run at any one time. For example, if you are doing like a 1080p video in Adobe Premiere Pro, which I've done for my old job, that program will hog every single resource it can get its hands on. So that's the only program that's working when I'm doing rendering a video, for example. Now, what this picture here is a simulation of the CPU in my Samsung Galaxy S10. So this is an 8-core processor, but it's split down into 3 categories. So we have 2.2 times 2.73 gigahertz Mongoose processors, 2 times 2.31 gigahertz A75 processors, and then 4 times 1.95 gigahertz Cortex A55 processors. Now, I'm not an expert on these things, but I will suggest that the middle one will handle graphics for games. The last one, I'm not too sure. I'm not really sure. I suspect the first one, the one with the highest clock speed, will be the one that does like opening your apps, managing memory, makes the phone feel fast. As an aside, here's the CPU in my laptop, which, on paper, you would think, on first glance rather, you would think a more capable device. But the overall clock speed is on average down compared with my phone, and it's only a dual core processor where I've got 8 cores in my phone. So the reality is my mobile phone, or if you have something similar, or like a current, the last 1 or 2 iPhones, the chances are the processor in there is actually more powerful. In theory, my phone or your phone could possibly, if you docked it, there's little docks you can get for them and hook it up to a monitor and a keyboard and stuff. That would probably, in theory, on paper at least, perform better than this laptop. Not that I'm inclined to do that, and the laptop's obviously more convenient, but that's just an idea of my little laptop there. So, summarising the features of a CPU, High performance CPUs will have a higher clock speed, and they'll also have multiple cores, meaning they can run more instructions at the same time. Low performance CPUs, the kind you'll find in very cheap like netbooks. If you get a netbook from, that's a small laptop by the way, a netbook from Currys or Argos or wherever, Amazon, quite a level low performance CPU. I'll only have 1 or 2 cores in the processor, excuse me, and it'll have a lower clock speed as well, which means that's what makes it cheaper. Obviously performance will suffer as a result. Right, the bit that's going to take some explanation. Now, before you panic about this picture of Little Man Computer, I have tested this on my own phone. It does work. It's not the easiest thing to see, but you don't need a laptop or a tablet or a computer to get to it. It will work on your phone, just to reassure you. So this is a website called Little Man Computer, where it's a visual representation of what happens inside a CPU when it's running instructions. So on this section on the left, that's where you're going to write your program. Don't worry about the code to use. It's where it says assembly language code. That is what's called a low-level programming language. What that means is, it means very little to humans, but it is exactly what the CPU wants or can understand. When you program in Python or Scratch, that's a high-level programming language. What that means is, high-level means it's designed to be read by humans. So Python's a high-level one. Inside, we use idle to do our Python programming. In idle, we don't know it or don't need to know that it actually translates it from Python into a low-level language that when we run it to do a little calculator or a little program, idle will convert it into machine code, assembly language code that the CPU can understand. It all happens in fractions of a second because we have powerful computers, but that's what it is. We program in Python. That's a high-level language, which means we can read it. You understand what like print and output and input and things like that mean. In this one, you don't have no idea what the code is. You don't really need to know unless you really want to get into it. But that's why it's got assembly language code. And the codes that you're going to use, don't worry about that. I'll give you all those shortly. Again, remember this is a video. You can rewind it anytime you want to rerun over anything that doesn't necessarily make sense the first time. On the right hand side, the RAM section, little green sticks of RAM that go on your computer, this is what the CPU sees, little banks of information with data, lots of ones and zeros, funnily enough. I'm sure that sounds familiar. In the middle, the CPU, that's the actual brain, that's the CPU, what it's doing. Different sections, got a program counter, an instruction register, an address register, and an accumulator. The accumulator is not actually a bet your dad might put on at the bookies. Excuse me. It's just where it's storing a number of operations that have been handled. Next, at the top and the bottom, we have input and output areas. And then at the bottom, look, an Android looking symbol. This is what the computer is actually doing. Your task today then. I suggest you rewatch the video if it doesn't make sense, which is quite likely because it took me a few goes to understand this completely. So on this little slide here, we have some assembly language code that you're going to copy in to the Little Man Computer. I will put the link to Little Man Computer on Show My Homework, so you don't have to copy it down from here. But there's the code. So it's IMP, next line, STA space 99, blah, blah, blah. What I want you to do is put that in and run it and see what happens, basically. On the next slide, there are some extra commands you can use if you want to try and make your own one up, if you're feeling that way inclined. But the main activity, your turn as it were, is to put these in, and there'll be a worksheet to answer these on. You don't necessarily need to get your own notebook or anything. I will put the worksheet on Show My Homework as well, or you should have seen it because you'll have obviously opened up Show My Homework to get the link to watch this video. So yeah, what I'd like to do is put the code in, watch it run, and then answer the questions on the worksheet. You can either just write the questions down onto paper and then answer them. We can print them off if you have access to a printer. I don't really mind as long as you're able to prove to me somehow you've done the work. There's also, if you want to do some extension work, there are some other programs already written for the LMC using a drop down. Have a look at them and see what you think. Like I say, it's a longer video today because I think explaining the Little Man Computer takes a bit more time. And then I'm not going to explain what the codes do. I think sort of like INP, add, out, fairly straightforward. But I'll leave you to it. As always, if you have any questions, message me on Show My Homework or send me an email. Good luck, and I will speak to you guys next week.